Hello, welcome to this session where the topic of interest of the only thing we're going to talk of absolute certainty is the topic of uncertainty. I'm now going to try and examine and introduce some of the underlying issues of probability which drive the ideals of quantum mechanics. You can see from the cartoon just above me, Heisenberg's Department of Physics, the map saying you are probably here. Later on we're going to discuss something known as Heisenberg's uncertainty principle, which considers the fact that when making measurements of certain objects we cannot be completely certain of the location without compromising other observable factors. So let's start off where this thinking began, I suppose. It began with a man known as Erwin Schrodinger. Some of you may recognize this name as being associated with Schrodinger's cat. This is a thought experiment which considered if a cat was placed into a box containing poison or a radioactive source which is likely to decay and kill the cat, is the cat alive or dead? This theory or the thinking goes that the cat is simultaneously both alive and dead. Both states are possible until an observer comes along and opens up the box, and then we observe to what point that's collapsed down into. So that's some thinking which Schrodinger inspired. Let's start off with what he originally did. He kind of developed an improvement on the idea of atomic energy levels. He presented a kind of an advanced quantum description. And what we had here was that energy levels still existed, but objects or the electrons within the energy levels were described by something called the Schrodinger equation. The Schrodinger equation, and we don't need to go into too much detail, but is to say we'll describe an electron by something known as a wave function. So this is a function of both location and time. Okay, so a function of both location and time. And as it happens, this wave function, which describes our electrons, if we take the square of this wave function, we get a probability of where an electron might be. This is the key feature here. Gives us the probability of where an electron might be. So we have a function which describes atomic energy levels very effectively, but when we square it, it reveals that there's only a likelihood of an electron being in a certain location. So let me show you how this develops in a little bit more detail. Schrodinger's atom produces kind of electron clouds. These are areas where there's most likely to be the location of an electron. We see here we've got to imagine this as a three-dimensional structure, and the clouds where the most likely for electrons to occur have been shown on the diagram. The model also does show orbits and energy levels. So the model in fact fits both of these situations. In fact, the energy levels are described so effectively by Schrodinger's equation. When it's applied, it precisely predicts Balmer's formula. Now I mentioned when I was looking at atomic spectra that Balmer's formula was a formula which described some of the emission spectra of hydrogen, which he'd got to pretty much by checking, guessing. There was no possible scientific explanation. But suddenly Schrodinger's equation produces Schrodinger's atom, which has these electric clouds, but also orbits, and the idea of orbits and transition between orbits, which we could see and we observed with emission spectra, can now be explained using Schrodinger's thinking. So this is a big step forward in mapping out some of the things which have been observed previously. Now, probability shown graphically. I guess I should explain this a little bit. What we have here is I've got a number of diagrams just to show that what electron probability really means. I've got electron probability, and we see these blurred diagrams or kind of blurry areas, what each one of those spots indicates is the likelihood of an electron existing. And this 1s, 2s, and 3s are actually relating to the first shell, or the second shell, or the third shell around potentially around a hydrogen atom. Now, for the lower, smaller atoms, the step forward wasn't as great, but what we discover is that Schrodinger's equations really effectively describe much more complicated, larger atoms. And we see here we have these diagrams showing the most likely position of atoms depending on which shell they're in. So that's just a graphical interpretation of what Schrodinger had found out. The next step, we have Werner Heisenberg. Now, Heisenberg stated, it's not possible to measure simultaneously the position and the momentum of something with indefinite precision. Now, we'll come to this in more detail in a moment, but just imagine you're in a completely darkened room and you're searching for a tennis ball. Now, what would happen is that you would stumble around the darkened room trying to find the tennis ball, and at the point when you come into contact with the tennis ball and you think, okay, that means I've got the position, I know what the position is, at the moment in time you're obviously going to knock the tennis ball and therefore the momentum is going to change. This is just a simple idea to try and show how it's difficult to confirm both these values at the same time. If we think about it mathematically, Heisenberg presented a position uncertainty principle, and this was a formula. He recognized that the uncertainty of the location of position multiplied by the uncertainty location of the momentum was always going to be greater or equal than a Planck's constant divided by 4 pi. So this was the hypothesis which he put forward. Now let's try and put this into action. So I'm going to introduce a question which is show how you can actually use this information. My uncertainty question considers the velocity of an electron, which has been measured to be 1.0 times 10 to the 6 meters per second plus or minus 0.01 times 10 to the 6 meters per second. I'm asked to find the maximum precision that can be given in a simultaneous measurement of position. So go through the facts. I know that my uncertainty of velocity is 1%. 0.01 divided by 1 times 100. The momentum can be given as the mass of the electron times the velocity, which gives me 9.1 times 10 to the minus 25 kilograms meters per second. The uncertainty of this, if I take 1% of that value, gives me 9.1 times 10 to the minus 27 kilogram meters per second. Uncertainty principle states, so therefore if I rearrange this for the uncertainty of position, I can find out that my uncertainty position is going to be plus or minus 5.8 times 10 to the minus 9 meters. That's as precise as I can be. The uncertainty position is useful. This can be further added to. There's a further equation called the energy uncertainty principle. Now, this tells if a particle remains in a certain state for a long time, it will have a well-defined energy, but if it remains in the state for a short time, then the uncertainty of the energy is going to be larger. And it's actually quite useful for working out the intensity of different emission spectra and why that's different. The formula we see here is the uncertainty in the energy multiplied by the uncertainty in the time interval is going to always be greater or equal than Planck's constant divided by 4 pi. And that gives you a full breakdown of the ideas of uncertainty which underlie quantum mechanics.